Now in this lecture, we're going to look at the graphs of the secant and the cosecant functions. So we're going to start out by graphing y equals secant x, and remember secant is a reciprocal of cosine. So what I've done here is use the same x values that we did for the tangent and cotangent graphs, but now we'll use the reciprocal identities, remembering that secant is the reciprocal of cosine, and then we just take the reciprocals of all the cosine values. So for example, when x is 0, cosine of x is 1, the secant will also be 1. When x is pi over 4, cosine will be 1 over square root of 2, or square root of 2 over 2 if you prefer. Reciprocal will be the square root of 2, which is about 1.4. Notably, any place the cosine is 0, so these will be the odd multiples of pi over 2, so in this case pi over 2 and 3 pi over 2. Cosine is 0, and the secant values are undefined. Okay, so the first thing we want to note when we put together the graph of the secant function is that we're going to have, just like with the tangent graph, vertical asymptotes at all the odd multiples of pi over 2. Okay, all those angles that would on the unit circle lie on the y-axis, where cosine is 0, secant will be undefined. Okay, and then we note that when x is 0, y is 1. When x is pi over 4, y is going to be a little bit more than 1, about 1.4. When x is 3 pi over 4, y is going to be a little less than 1, negative square root of 2. When x is pi, y will be negative 1. So then if we go to 3 pi over 4 and 5 pi over 4, note that the y values are both negative square root of 2, which will be a little below negative 1. And then when x is 7 pi over 4, y is square root of 2. When x is 2 pi, y is 1. Okay, and then if we want to do some coterminal angles, note that if we went to the right by 1 more pi over 4, we went to 9 pi over 4. That's coterminal with pi over 4, so we're going to have another y value at square root of 2. And if we work backwards, negative pi over 4 is coterminal with 7 pi over 4. Okay, so again, the y value will be square root of 2, so a little greater than 1. Okay, so now if we connect the dots, we're going to see similar behavior to what we had with the tangent and cotangent graph, but now we're going to have turning around. We're going to have relative mins and maxes. So for example, if we start at x equals 0 and we increase x to pi over 2, our cosine values are going to be positive, and therefore the secant values are also going to be positive. And as that cosine approaches 0, the secant is going to approach positive infinity. And similarly, if we go backwards, now we're going to be in the fourth quadrant with these negative angles. In the fourth quadrant, the cosine and the secant will remain positive, and therefore our secant values will again go up to positive infinity as our cosine values approach 0. Between pi over 2 and 3 pi over 2, we're going to have similar behavior, but now we're in the second and third quadrant where the cosine and similarly the secant values are negative, and therefore as we approach these vertical asymptotes, our secant values are going to go to negative infinity. And then over here we're in the fourth and then the first quadrant again, and then over here this would be at 5 pi over 2, we would have one more vertical asymptote we could draw. We get basically a repeat of the behavior we had in our fourth and first quadrant angles over here. Okay, so the graph of the secant function is going to look something like this. Okay, so now we have a third classification of graphs. We had the sine and cosine graphs, which were very similar looking. They were both waves. We had the tangent and cotangent graphs, which were both kind of these S-shaped curves with a period of pi. Secant and cosecant, it will turn out, have very similar shapes. Okay, so a few things we want to note about this graph. The first is our domain. So here, just like with the tangent graph, we want to avoid dividing by 0, and we divide by 0 when cosine x equals 0. So in this case, the domain is all x, except when x is an odd multiple of pi over 2. Okay, exactly the same as the tangent domain. Okay, if we look at the range, we have two pieces of our range. Note that there's nothing between -1 and +1 here. This is all empty space. So we have this negative piece that goes from -infinity to -2. And then we have this, sorry, not -2, -1. So we have this negative piece that goes from -infinity to -1. And then we have this positive piece that goes from 1 to infinity. Okay, so this is how we would write it in interval notation. So this means that we attain the endpoints -1 and 1 because we do have y values of -1 and +1 on our graph. And then we have these two non-intersecting intervals that we stick together using a union sign. Or if we want to write this using inequalities, we'd have y is less than or equal to 1 or y greater than or equal to +1. Okay, so that's going to be the range. Just like sine, cosine, tangent, and cotangent, the secant graph is periodic, and our period is back to being 2 pi. Okay, because now, we could take this bit here between -pi/2 and 3 pi/2. That's going to be one period. We have to cycle through the positive part and the negative part, and then we can start over. So the period will be 2 pi. And just like its reciprocal function, we see the symmetry about the y-axis, so the secant graph is even. Okay, so out of our 6 fundamental trig functions, we have 2 of them that are even, secant and cosine. The other 4 are odd, sine, cosecant, tangent, cotangent. Okay, so that's the graph of the secant function. Graph of the cosecant is going to be really similar. So we'll use a similar process from when we went from tangent to cotangent. So now we'll just look at the reciprocals of the sines. And we'll see a similar shape emerge. We'll see different domain. We'll see the same range. And these are cofunctions of each other, so because of our cofunction identities, the cofunction graphs have very similar properties. Okay. So now if we look at the graph of the cosecant, we want to ignore the cosine column and only look at the sine column. Okay, so now when x is 0, sine is 0, cosecant is undefined. When x is pi/4, sine is 1/√2, cosecant is √2, which is again a little bigger than 1. When x is pi/2, sine is 1, cosecant is 1. When x is 3 pi/4, secant will be square root of 2, cosecant will be square root of 2 rather. When x is pi, sine is 0, so cosecant is undefined. When x is 5 pi/4, sine is 1/√2, negative 1/√2 rather. Cosecant is negative square root of 2. When x is 3 pi/2, sine is -1, so cosecant is -1. When x is 7 pi/4, sine is negative 1/√2, so cosecant is -√2. When x is 2 pi, sine is 0, so cosecant is undefined. Okay, so in terms of asymptotes, now we're going to see something that looks very similar to our cotangent graph. Okay, so we're going to start out with a vertical asymptote along the y-axis when x is equal to 0. Okay, so this is y equals the cosecant of x. Okay, we're going to have a vertical asymptote at x equals 2 pi and at x equals pi. Okay, so now all the places where sine is equal to 0. Okay, when x is pi over 2, we see that y is 1. When x is 3 pi over 2, y is negative 1. When x is pi over 4 or 3 pi over 4, okay, so this would be when we're in the first and second quadrants, y is square root of 2. Okay, so that's going to be a little bigger than 1. When x is 5 pi over 4 or 7 pi over 4, okay, that's third and fourth quadrants, y is going to be negative square root of 2, and that's going to be a little less than negative 1. And now if we connect our dots, this will give us one period of the cosecant graph. So we have the same behavior of going up to infinity or down to minus infinity as we approach our vertical asymptotes. We see that the cosecant and the secant graphs have the same shape. They're just offset a little bit horizontally. Both have a period of 2 pi. Both have the same range. The domain for the cosecant graph is now everything except for the integer multiples of pi, the places where the sine values are equal to 0. This was the same domain that we saw for the cotangent function. And just like with the secant graph, we have these relative minima at y equals 1 and the relative maxima at y equals negative 1. So we have this sort of turning around behavior. Okay, so this is the basic graph of the cosecant. It may not be easy to tell here because I only did this one period to the right-hand side of the y-axis, but the cosecant graph is actually odd, and therefore cosecant of negative x is equal to negative the cosecant of x. Okay, and we could see that also because cosecant is a reciprocal of sine, and the reciprocal of an odd function is odd, and the reciprocal of an even function is even. So that's why the secant was even. Okay, so that's the basic video for secant and cosecant. In a future video, we'll talk about how to do a manipulation of secant and cosecant. And it's really straightforward if you can do a manipulation of a sine and cosine graph, because then you can just take reciprocals, plot points, and then remember the overall shape of a secant or cosecant graph.